Hi everyone. For this workshop, I'd like to discuss about hardware design issue associated with the physical services. As we know, most intelligent systems are focusing on information, like all IT technologies are all focusing on how can we deliver information as quick as possible, how can we deliver it as efficient as possible, as convenient as possible. And all these new technologies are focusing on how to create a content or how to deliver proper information to the proper users. But as we know, many services are uh, emerging in a offline world, which is mostly physical services. You can think about delivery, home security, smart factory, farming, construction, disaster response, elderly care, many things you can think about. Um, so we have to think about how to connect this like online or digital services into the physical world. But as we know, our hardware or our robotic systems are not quite ready to deal with this physical world. Um, it's primarily because of our legacy, which is manufacturing systems. Most are robotic systems designed to deal with the manufacturing. And as you see in the DARPA Robotics Challenge, all these robots are look like a human and look like a superhero, but those mechanical components are actually taken from a factory and automation. And those are primarily focusing on like high position accuracy without worrying about collision. They're not designed to make a contact in a dynamic fashion. Whereas, you know, animals world, as all of us are designed to actually deal with the contact and impact all the time. Are we as accurate as those machines? Probably not. Are we as accurate as a position control or force control? Probably not. But we're pretty accurate at something else. I cannot really put in a word on it. Like, so maybe it's balance, maybe some sort of abstraction. We have a much better abstraction about like doing a task. Um, I just lumped all these intelligence. I start calling as a physical intelligence. So I've been thinking about this issue last good 15 years and actively researching on this about 10 years to really try to make some transition from grounded, structured, well-known high precision task to unknown, unstructured environment where robot has to move around, cannot rely on like bolting on the ground, and has to rely on dynamic balance, had to rely on force control, had to deal with the collision and impact. How can we do this design paradigm shift from robot factory, like a factory setting, to more like unstructured environment like our home? So I'd like to talk about a few like effort to deal with this issue and looking back histories. So I cannot miss out like Victor Scheinman. He was actually teaching me when I was at Stanford. He was teaching one of the project-based class, and he's basically father of programmable ARM, computer program ARM, like 6DoF with the grippers, and he eventually designed the first Puma as well. And most industrial robots are actually descendant of his design. And interestingly, his first arm, like a Scheinman arm, was actually intended to do the force control and then dynamic contact. He was thinking about it, so it's actually designed to be very low gear ratio. But the practicality basically catch on that they want to have a high payload. They don't want to deal with any high impact. They want to have a higher precision, so you can actually achieve repeatability in the factory setting. So all these descendants of Scheinman arm are not actually capable of colliding or making contact with objects. So several approaches emerges. One of them is a direct drive. Harry Asada and other folks really thought of this idea, and then immediately it became industry standard for some application. So this SCARA arm is actually pretty popular in fast assembly process. It's pretty impressive. Like human cannot even catch up in this kind of level of precision and speed. And because direct drive, there's not much friction, and there's no gear, no backlash. The modeling is much more accurate, and then robot can perform much high precision and high speed. But these direct drive arm typically doesn't have a high torque. It's a payload issue. So as you can see, it's mostly aligned in the horizontal direction, and contact is mostly dealt by this suction cup, which actually has some soft cushion on it. So there's those direct drive arm is mostly designed for this high precision and high speed motion. Recently, there's a company called the Genesis Robotics, I think, start implementing this direct drive robot for this kind of force control and the contact issue. So they redesigned their robot to be very responsive, very fast. It's no longer a horizontal direction. The vertical direction can be really responsive without having force sensor. It's literally just motor itself can be sensor because it's direct drive. There's no gears, very low friction. So it will be interesting to see. But my simple feeling on it is the just of torque. It might not be enough. The direct drive, the electromagnetic actuator is inherently limited by the torque. The magnetic stress has saturation level. It can't go any further theoretically. So we eventually need to rely on the gears if you want to have a higher payload. Another approach is series elastic actuator. You probably heard about this term many times, and there are many robots are built out of this idea because it's kind of like bio-inspired. Like animals are built in a way that there's muscle, there's a tendon acts like a spring. Well, entire muscle is actually spring too. The entire animal bodies are kind of spring. So this idea was very exciting for many people. So there are some variations, but there's always spring in series with the actuator, so it can actually handle impact. It can mitigate the impact forces. We don't know, cannot really have any conclusive answer for where this technology is, where it's going. There are several very successful robots out of this technology. One caveat is the control bandwidth is inherently coupled with its stiffness. So you gotta be very careful choosing the stiffness. If you want to have a very soft contact, safe contact, I want to reduce the stiffness. Now this entire system suffer from the bandwidth. As you can see in the plot, this is one of the cases. You can model different way. And if you reduce the spring constant, your lowest the vibration mode frequency is going down. So your force control bandwidth drops. That's why all these heavy, big humanoid machines, they're actually rely on very stiff spring. Then now you have to deal with this the contact issue again. So there's very tricky design issue on a series elastic actuator. Hydraulics, we cannot miss hydraulics because hydraulics are designed to deal with impact and digging ground and all kinds of heavy machinery designed out of hydraulics. And not necessarily kind of delicate way, and not necessarily the hydraulics are designed to be very gentle and soft and on contact. It's more like is robust against contact because the shock are distributed through the fluid instead of gear, train, or particular components. And BDI and other folks like took it into the next level. They designed their controllers, the servo valve, for example, the pressure controller into the next level, much higher bandwidth, so they can be actually delicate. So there the first spot is actually hydraulic, and now the famous Atlas robot is all full hydraulic. They designed their custom power unit, and then they designed their custom pressure controller, so they can be relatively accurate in force control. I don't know all the details, but according to their performance, they are be able to, these robots can control the forces pretty well. So it'll be interesting to see where this technology goes. This is our approach. since 2009, 2008, we thought of like how can we achieve a high force and high backdropability. That's what people use, and we actually start saying that don't use backdropability. It's primarily inspired from Phantom, the haptic device that designed to display force of on human hand when human is manipulating some virtual object in the virtual world. You can actually get force feedback on it, and then it's commercialized for surgeon training program and so on. And we actually use as a like a leg, as you can see in the MIT Cheetah is all four versions of MIT Cheetahs are using this technology to mitigate the impact and then uh, increase the accuracy in force control. Because if you cannot handle impact, if you're rigid or if you're too heavy, you basically cannot control the contact force. And then in locomotion, if you cannot control the contact force, you're not doing anything. You can't really do the force control of the robot. So basically, idea is to optimize the design of the system in a way that minimize the task space mass matrix while maximizing the torque density of the system. And basically give up the force feedback. So having a force sensor at the end effector and then getting force feedback is inherently a dangerous idea. It's very easily go unstable. I'll talk about it in the next slide. But we basically decide to rely on just purely feed-forward force control. That allow us to actually do a more aggressive contact making instead of relying on force control and then limit its performance. So I will briefly show you some of these videos from Cheetah, and hopefully you can take a look at this video as a different perspective, looking at it as a like machine that can actually handle impact and can absorb shocks. So typically, wow, this like looks like a dog, but you have to think about like electric machine that can actually be this powerful and this powerful in negative way. Like it can generate that much power, but also absorb that much power without damaging any components. So before this Cheetah 2, everybody thought like electric robot cannot run because they're so stiff, they're so powerless. It's actually not true. The electric motors are actually about 100 times more powerful than mammalian muscles. It's just designing such a system, it can be a little tricky. So this is Cheetah 3. Here we start using a more accurate model-based controller. And this is this video from the MPC. So we can not only just go forward, we can do many different gates, including stair climbing, and this is blind actually. So every step, the robot actually gain information from the collision to the environment. So these kind of model-based approaches, you can simply predict, cannot be achieved without having reasonably accurate force control. And any of these contact is very dynamic. It's like there's always ground contact period followed by the impact. So if you don't have that kind of bandwidth, or if your system go unstable through that kind of high bandwidth event, you can't achieve what you're trying to do. So I'm talking about leg robot here, but any robot that has to deal with the contacts and dynamic impact, the hardware is actually very critical. And that will limit what you can do and how fast you can do it. This is more recent result where our controllers actually rely on like specialized tool. It's called the RPC, regularized model predictive control. We actually come up with a way to update our cost function, because whatever optimization we use, the cost function is representing the abstraction of like whatever your task is. In our case, is running well, walking well is our task, but very abstract. But you have to represent that with a function, typically is following a trajectory or some sort. Not necessarily precisely representing walking well. So, but following a body trajectory was reasonably good, but it's not good enough to achieve these kind of all kinds of behaviors. So we have to actually change our cost function to be more precisely representing what we want. So our student Gerardo actually come up with a way to gain information from data and then update our cost function to be more accurate. I think everybody probably experienced this kind of issue whenever you trying to do something, and then we had our own guess of cost function, no matter what optimization tool or machine learning tool you use, and then often that's not what you exactly want, and the cost function is getting more complex and complex. And locomotion case is actually reasonably simple, but if you are trying to do something more complex, that can be very tricky. So I'll talk about it a little bit later as well. Almost done. So for those who are not very familiar with this issue, I will explain very briefly. The reason why industrial robots are not designed to make a contact, or it's not good for doing contact-rich tasks, because it's apparent is a operation space inertia is way too big. People call that, oh, their robot is very stiff. Robot is very stiff. We need a soft robot. It's actually not stiffness issue. We want actually high stiffness to achieve high bandwidth. The issue is not stiffness. The issue is actually inertia. So what I mean by inertia, like if you have a robot body, either it can be anchored on the ground or like a floating body like our leg robot, you're going to have some manipulator, which is represented as brown piece. And when you make a contact with the ground, the arm or manipulator should react or observe shock in certain fashion, depending on the algorithm. But the issue is you have to not only deal with the mass of inertia of this manipulator, you also need to deal with the rotor inertia. How big is the rotor? And everybody say, oh, the rotor is very small, rotor is very light. But actually, in reality, rotor inertia actually dominate most robots. So it's more like this. If I draw a cartoon, imagine you have a body with this rack and pinion, and then pinion has this gigantic circular piece, which is not very heavy, but it's very large inertia, large moment of inertia. In that case, if you're blind, if you close your eyes and touch the tip of the manipulator, you'll feel much heavier feel than this brown piece. You're going to feel reflected inertia from this rotor. And so our design philosophy is all about how to minimize that without sacrificing or minimally sacrificing our torque control issue, torque density. In industrial robot, they really want to achieve a high accuracy in the position. So they actually have a very high gear ratio, and there's a lot of friction on it. And if I give you an example for our system, the inertia ratio between the length, the mass of the manipulator, to the rotor inertia is actually about 1:1. But that's because we have a 6:1 gear reduction. And most industrial robot arm has like 100:1, 200:1, 300:1 gear reduction with a very high friction system. So in most robotic system, when you hit something, when you in manipulator collide with an object or on the ground, the impact force is pretty much dominated by the rotor inertia. but this is not very well addressed by many people, because if you're using any simulation tool, my guess is most of you are using simulation tool. 99% chance your simulation tool doesn't actually have the rotor inertia in your model, because using articulated body algorithm, including rotor inertia, is actually quite tricky. But in our dynamic simulation, we actually include that. Otherwise, it's not going to be accurate. So people use the term backdrivability. Oh, that road is backdrivable. That's not backdrivable. But there's no proper quantities defined, and there's no normalization. Like, you can't really say backdrive just feeling by finger when you deal with a 1 kilogram robot to 100 kilogram robot, sometimes a 10,000 kilogram robot. So we introduce a new terminology, which is impact mitigation factor, which is normalized inertia quantity, which is most important component of the impedance of your robot. Impedance, is comprised of like acceleration dependent component, which is inertia, and velocity dependent component, which is viscosity, and position dependent, typically spring. When it comes to this impact issue, there should be no spring, and there's going to be some viscosity through bearings and so on. That should be also minimized. It's not trade-off issue. Inertia is the most important design component where there's a design trade-off. So we basically define this IMF as a proper representation of force transparency, or backdrivability we use as a kind of casual term. It's formulated this way. It's actually pretty simple in high level. Basically, we basically compare your real reflective inertia, real operation space mass matrix. If you calculate your mass matrix at the end effector, you're going to get real mass matrix. And then if you have some impact with some velocity, your impact force will be proportional to your inertia matrix, mass matrix times velocity vector. But how can we quantify that? Like, how good it is, like how well they observe shock, or how badly observe shock. We have to compare with something. We cannot compare with the standardized number. So we decide to compare with the worst case scenario, which is when everything is locked. Imagine our cheetah is jumping and landing, and then when every joints are locked, your foot is gonna hit or get the forces as if like a sculpture is hitting on the ground. So that's where the your mass matrix actually get worse. Your impact force is going to get worse. So we plot the worst case scenario of mass matrix, and then compare that with the real mass matrix, and then that's how we quantify IMF. This is IMF is one number, and you can't just quantify the impact mitigation factor of the manipulator with just one number, because what if we push it to the left? What if we push it to the up? What if we push it to a different direction? What if you apply a wrench? So IMF, you can actually don't do this like determinant term. You can actually tease out. You can apply certain. You can take a look at a certain direction only, and then you can also take a look at that as well. And you can use this IMF term for anchored, like a grounded robot as well. How can you do that? If you anchor all this joint, your mass matrix is going to go to infinity. So also, just in order to be fair and then normalize, you have to imagine the manipulator anchor on the ground. You have to detach from the ground, and then you can calculate it, and then you are going to get reasonably well represented backdrivability through IMF. So looking back, this is like 20 plus years, and looking at all these leggy robots, there's no manipulator, because there's actually not many manipulator that does any contact-rich task dynamically. If you look at the green square, those are hydraulic robots. At some point, hydraulic robots are actually dominant, like, because there's a big dog post dynamics robots are doing amazing things where very minimal thing going on in electric robot, except Ashimo. Ashimo was pretty impressive. We don't know all the things going on in there. But we believe that Ashimo actually used very the non-backdroppable, very rigid, low IMF actuator. Um, and the ETH started using surge elastic, which is actually a fantastic idea to do the proper force control and do the impact mitigation. And then after that, we actually started using our proprioceptive actuator idea to prove that the electric robot can be actually very dynamic, very powerful. And as we present our Cheetah robots, there's a couple of the Sirius last robot pops up, and Boston Dynamics approach was very hybrid, very complex. And nowadays, as you can see, there are a bunch of other companies are following our proprioceptive approach in low gear ratio with a properly shaped inertia. And now I cannot even count how many robots are actually using this paradigm. Whereas there's only one hydraulic robots exists where humanoid need many degree of freedom, and then they really want to achieve very dynamic capability. So they absolutely need the hydraulics. But so far, it looks like a proprioceptive actuator is pretty good solution for any contact-rich task. I'd like to show you a simple teleoperation video. This is bilateral teleoperation. There's no force sensors, there are feedback. These are just all feed for forward force control. But with simple algorithm, you can actually feel all the forces of the other arm. So I actually can feel the forces of the other hand with the limitation, because I'm not only feeling that force, I'm feeling all the acceleration inertial forces of the two arms. So I don't feel the impact. The forces are, there's a stiffness limitation. So I can feel like a steel. I feel like some sort of rubber. But perception allows us to do this without worrying about going unstable, because there's no feedback going on in the force sensor. The force feedback on this contact-rich task has been studied for a long time, and there are many people who tried it. But eventually, the bottom line is you can deal with the force tracking, whatever force you want to achieve, beyond the bandwidth of the actuator. But if you think about this kind of system and the force bandwidth is very poor. Our system is probably one of the highest, and our system can achieve force bandwidth about 40 hertz or 50 hertz. And most manipulator force bandwidth is like 2 hertz and 3 hertz. And how can you even think about making a contact? No matter what force sensor you use, no matter what the algorithm you use, you can achieve a higher bandwidth than you actually can do. So that's why all these things go unstable, and then delay is going to make it even worse. If you combine proprioceptive actuator with some tactile sensor, this is actually our tactile sensor as well, that give us XYZ force and then contact location. And this is also designed to actually do the contact-rich task, like impact and then high forces. There's no inertial noise. It can shake. So I'd like to show you what you can do if you combine those. So there's no fancy planning optimization whatsoever. This is just represent, this algorithm is just representing an abstraction of maintaining a contact with the brick. That's all it does. And then you don't need fancy line. There's only one line in this code, but you can achieve a high bandwidth. And then going through the impact, it doesn't go stable. To think about if you have this kind of high bandwidth system, and imagine each finger of your robotic hand can do this kind of thing. As soon as you hit something, an object can actually keep maintaining in contact. All these low-level abstraction is going to help a lot in the future when you do like content-rich tasks. Yeah. How about, we talked about arms all the time, and how about hand? Honestly, the hand is actually even more important. We think human arms or animal legs are actually near ideal. They're fantastic. I agree. Our muscles have a very little inertia. We have a very little reflected inertia. So when you collide something, our arm doesn't necessarily appear to be very, very heavy because their muscle doesn't impose a higher inertia. But still, I don't want to deal with all the things with my wrist because it hurts and probably eventually will damage it. But our finger act such as is amazing shock absorber. So you probably are not conscious when you're opening doors and grabbing your phones and grabbing your chair. Your hands are constantly making impact or collision, high velocity collision with those objects. You're not even aware of it because your hands are such a low inertia and then well designed, and there's some low level controller I don't even know do these things. So recently, it's all 2019. There are people are start using this high bandwidth, high IMF hands. One of them is CMU. Aaron Johnson and Matt Mason designed this direct drive.
Design is mechanically simple.
But pretty much the same idea. They're trying to be more reactive and can be more conforming, especially something like this kind of behavior. You don't need to be like super accurate. Just, the proprioception will tell you I'm in a contact, and then you can just react upon it. And then hit the ground, and then you read that. Oh, okay, now I'm hit the ground, so I'm going to just grab it. So you can achieve such behavior much faster without worrying about damaging and breaking. Similar idea, Youngjae Kim, he's been designing. He's an amazing hand designer. He designed many hands, and this less than 2 kilogram hand, 15-degree freedom hand, can actually do quite amazing precision of control. Not as low IMF, high IMF like direct drive arm, but it's much more versatile, and it can handle impacts and overstretch without getting damaged. Primarily due to his ingenious design of cable mechanisms. And he also used low gear ratio, like a 25-to-1 gear ratio. And not only this precise and then impact resistant, it can also do pretty heavy duty activities. So design is getting there, and well, with the exceptional designer, I guess there are still, we need to have a much better algorithm, much better representation of abstraction associated with this physical task where we cannot even put words on it. So along with the high IMF hands, high IMF arms, or if you have a proper algorithm, you can do something much more impressive than what we've seen. So, along the line, I would like to show my hand. This is me picking an apple blindly, completely blindly. And so I want you to see what happened if you haven't seen before. It's pretty fast, but this is how dumb my hand is. I have no idea what I'm doing. But if you hit something, first of all, because I'm not looking at it. And somebody might say, oh, Sangbae, why you're not looking at it? We always look at things, do this. I guarantee you, when you pick up something, you're not looking at your finger. You're not looking at the distance between your object and your finger, and then visual surveying. You're literally just throwing your hand, and the hand is doing almost everything. So here, my hand collide with a few apples, and then if you are clever about it, if you have a good sensor back of my finger, you can estimate where the apple is, and then run some optimization, choose the proper apple. It doesn't work that way. Literally just hit something. As soon as hit something, just try to grasp, try to make it aggressive. And then of course, that's not the ideal location, and then failed it. Sorry about that. Hit, and then try to grasp, and there's nothing. That's not a good location. I don't know why we run this way, but it does. And then while you're doing it, while you attempt to make aggressive, it make a contact with like 3 more apples. And then, okay, you can also think about, okay, I am making contact with the 5 apples. Why don't I choose something the easiest? Apparently, my hand choose to pick up something the hardest, the bottom one. And this is making a bunch of contact. And then, okay, I'm gonna decide to move down and grasp the bottom one. But obviously, it's the bottom one, so it's not very good posture. So I have to make an adjustment on my hand posture by digging in. You have to dig in. So this is not a good posture. What if I fail? So I have to go inside more, pushing the other apples, and then bring it out. The whole thing happens about 0.5 second, 0.6 second. If you look at individual, the decision making, it's not ideal. Is it good enough? I'm not even sure that's good enough. But overall, we never fail. I can probably pick up 1,000 apples like this. Uh, this is not going to be the very often times, but many times I can pick up like this, and then you probably succeed. So it's not about like what is the optimal trajectory, what is the optimal force. It's about how to make these discrete decisions, but each decision doesn't need to be that good. It's more of like how can we achieve this high level abstraction, pick an apple, which can be very concretely defined, but in this case, it's not. In many cases, your goal is just to bring an apple. I don't really care how you bring an apple. So think about how can we even describe this kind of intelligence? You probably can think of many other cases like this. You're uh, bringing a key out of your pocket, and then you have no idea what your finger is doing. Like your finger is doing galloping with the foreleg, and then crawling, digging between your keys and key fob and your coins, and doing some like like finding the hook or finding the feature to grasp. If you bring your key out from your pocket 100 times, you're doing 100 times differently. It's going to be every single time it's going to be different. But our sort of sub-level intelligence knows what the goal is, and I'm not really sure we can put that as some sort of cost function. It's some very high level abstraction we're running upon, or our organism running based on. Um, like we describe things in our languages, and then soon you realize how abstract our languages are. I just pick on a verb, spread, which is actually, it turns out that is not that bad. You can, if you read those definitions, they're actually quite consistent. There are, some geometry. We can describe as some sort of geometry of the end result of some substance or something. But how to do it is very abstract. If I say spread a leg, spread the peanut butter on the bread, our brain knows what that means and then just find a way to do it. And how to do it is such a mess. You can do it with a knife. You can do it with a finger. We'll do it in a way that you will achieve it. And it's very difficult to even find a word to describe this kind of intelligence. So I think we need more of those to really advance this technology. I want to show you another pretty impressive video. I'm pretty sure we can do it if you're trained for a week, maybe not even a week, probably a few days. We can do this. I don't even know what's going on, so I would like to show you a slow motion. Think about like grasping, force closure, foam closure, trajectory optimization. I'm not really sure. Taking a look at this behavior or this task in a perspective of from optimality or some sort of cost function. How about collisions? How about rubbing forces? Yes, we need a good hardware. Hardware is gonna get there. It's still challenges, but get there. But eventually, I think the intelligence, physical intelligence, is gonna be the bottleneck. Eventually, we really believe that the elderly care is going to be a critical issue in the future society, where it's not like something we're developing a technology that like convenient for technology, like for us. Oh, it'd be great. It's okay not to have it. This is something we must have to stabilize our society, and it's not easy. If you look at this perfectly designed human is helping just a little bit weak person, and they have to constantly communicate and communicate through the contact. It's pretty challenging. I'd like to finish with a few points. Collision, has been, always something you need to avoid as much as possible. There are many tasks you can't really avoid. Yes, in the factory, they try their own best to avoid, and then they finish the job amazingly because it's a constructed environment. If you're going to unconstructed environment, it's or very versatile robot, it's going to be very difficult to avoid. So you have to deal with it, and you have to sometimes exploit it. You use as a information gathering opportunity. Um, in that case, high impact, high IMF machine is going to be essential. It could be surge elastic maybe, but, or our proprioceptive actuation, but you need to have a system that can have a very low inertia, so you can actually make contact and absorb shocks, and you can stabilize the contact and can do the thing, next task. And finally, we need to really think about like words and the tools, proper representation of the the concepts associated with this, the manual work or task, context task that is going to be very critical for any physical services in the future. Thank you for listening. I look forward to the panel session.